Okay, so this is, I think, the third video here. We are gonna actually do some integration by partial fractions. We're gonna do the one that we talked about in the last video, this integral of x plus 3 over x squared plus 4x minus 5. In the last video, I sort of talked about we need to reverse engineer this. The purple is integratable, the red is not. So, what I'm gonna do is do some work down here to just look at this fraction to like change the way it looks, and then at the end I'll come integrate it. So I've got x plus 3 over x squared plus 4x minus 5. So I'm just going to look at that thing. So if we look at this right here, and I start to walk backwards, the first thing that I want you to see is that the bottom of these are factored, right? I had an x plus 4 and an x minus 2. And that's going to get me this x plus 4 and this x plus 2. So the first thing I'm going to do is factor the bottom. I still have my x plus 3 in the bottom, or in the top. In the bottom, that factors to x plus 5 and x minus 1. So from there, and to be honest, this is a topic from pre-calculus that often, you run out of time in pre-calculus. So I've always wound up teaching it in calculus. But you learn that you can separate this out into something over x plus 5 plus something else over x minus 1. And you may say, wait, why can we do that? Well, these two would be combined, so there's a number. Actually, I'll write a capital A and a capital B. So A is a capital number and B is a capital number. Sorry, that made no sense. A is a capital letter that is representative of a number, and B is also a number. If you look at reverse engineering this 4x minus 2 came from combining two pieces. Well, what did those two pieces come from? Well, that came from multiplying by the common denominator. And I had a 1 in the top and a 3 in the bottom. If I had, the A and the B have to be numbers. If I had, for example, at the top of this one, an x plus 1, then when I had multiplied it by the x plus 4, and over the x plus 4, I would have got an x squared, which would have given me an x squared here, which would give me an x squared term here, and an x squared term here. Notice this is 1 degree less than this, right? And this has the same property. The bottom is 1 degree more than the bottom. So when I reverse engineer it back into the purple, I'm going to have the top be 1 degree less than the bottom. So since this is just linear with only an x and a number, then I go 1 degree less and I get a number. So that's kind of the reasoning why we can go and separate this out into two fractions. All I have to do now, going back to the purple, remember the purple was integratable, all I have to do now is figure out the a value and the b value that would go that would match up with this original fraction, and then I can integrate. The work is in finding the a value and the b value, and that's what I'm going to show you to do in a moment. So, what are we going to do? I keep referring to this previous problem, right? But what I'm going to do is almost exactly the same thing that we did right here on all this over here. So, and that'll help me figure out the a value and the b value. And you got to kind of follow the algebra to see it. If you were able to follow what happened here, then you should be able to follow what happens here. But instead of a 1 and a 3, I've got an a and a b. So let's do it. What I'm going to do is multiply this by x plus 5 over x plus 5. Hold on a moment. What that'll do is give me this common denominator in the b term in the second fraction. Notice x minus 1 times x plus 5. That matches this over here. For this one, I'm going to do the same thing, except for, you probably guessed it, I'm going to multiply by x minus 1 over x minus 1. And I'm going to put some parentheses there like that so that we can see that it's being multiplied by the whole thing. So I'm kind of working from here over. So I'm just going to write my x plus 3 over x minus 5 times x minus 1. That's equal to, all right, so on this right side, I've got fraction like this, x minus 1 times x plus 5 plus another fraction, x minus 1 times x plus 5. And in the top one, in the first one, I've got a times this thing. If I distribute that a in, I get ax minus a. This is getting a little weird, but just roll with it. And then the second one, if I distribute the b in, I get bx plus 5b. Okay, now, little fraction work. If I have 3/4 plus 2/4, I could add them to get, you guessed it, 5/4. So when I have the same denominator in two fractions, I can combine the tops into a single piece. The 5 is the 3 plus the 2. Notice this denominator matches this denominator, so I can combine those two into the same top, or in the same piece. The left side is going to stay the same, x plus 3 over x minus 5 times x minus 1 equals, all right, so what do I have? I've got, boom, I've got x minus 1 times x minus 5, or sorry, plus 5. And then look, I've got ax plus bx. I'm going to write it in that order. And then I've got minus a plus 5b. All right, now, another little fraction side thing here. All right, so side problem. Say I had x over 4 was equal to 11 over 4, and I asked you, what's x? I think you could reasonably say, oh, it's 11. What we're doing there is you're taking the tops. You're just ignoring the bottoms because of the same thing. You're saying x is equal to 11. If, say, for example, I had a different problem that said, x plus 1 over 4 was 11 over 4. You would set the tops equal to each other. X plus 1 equals 11, and you got x equals 10. That's the same thing I'm going to do here. I am going to just, whoops, I meant to change colors. Come on, green. I am just going to take the tops here and set them equal to each other. I'm going to ignore the whole denominators because the denominators are the same. Another way to do this would be to multiply on both sides by x minus 5, or sorry, x plus 5 times x minus 1. Why do I missed that too? Sorry, maybe you caught that. Anyway, what I'm going to get out of this, from this just setting the tops equal to each other, is x plus 3 equals ax plus bx minus a plus 5b. You may say, that's a little weird. Well, do you see I've got two x terms here? I've got ax plus bx, and then I've got two non-x terms. Well, I'm going to write this as x plus 3 equals, I'm going to factor my x out, open and close. What would I put in there? I would put in an a plus b. And then I get minus, or so I'm going to write plus negative a, come on, plus 5b. All right, now this is going to get a little weird. So, first off, you should agree with me that we have a 1 here in front of the x. Let me make that look better. 1 times x. All right, so now, here's the problem. We have three variables here, x's, a's, and b's. Ask yourself, thinking about going all the way back up to the beginning of the problem, what are we actually looking for? I'm not trying to solve for x here. I'm trying to figure out the a and the b so that I can then go and integrate this thing. So, a and b are what I'm looking for. But we have another problem. If you look at this right here, I'm trying to solve for a and b, but I only have one equation. So we have an out here, because normally if you have two variables you're trying to solve for, you need to have two equations in order to figure out what those variables are. But I'm going to try and convince you that we can build two equations here. You see that the 1 is the coefficient of the x here, and you see that the a plus b is the coefficient of the x. What I would argue to you is that 1 has to be equal to a plus b. Then I could do that with the 3 as well. The 3 over here is the only term that doesn't have an x. Well, what pieces over here don't have an x? Well, the a plus the 5b. So this, let's get this, the blue gave me this, and then I can get 3 is equal to minus a plus 5b. And that comes from this. So what I had was an equation with two variables in it, and what I did was I sort of ripped it apart into two different pieces, two different types of things that make up that equation, the two colors, and I built a system of equations. Now, talk about throwing back to algebra, it's a system of equations. At this point, we need to solve this system of equations to get the a and the b. This one's set up kind of nicely for us because we can use elimination. I get 4 equals, add the a and the negative a, they go away. Add the b and the 5b, I get 6b. From there, I can divide by 6 and get b equals 4 over 6, which could simplify to 2/3. Okay, so how do I find a? Well, I can take this and say 1 equals a plus 2/3. Solve for a, subtract 2/3 on both sides. I get a equals 1 minus 2/3, and that gives me 1/3. So what do I have? I have a equals 1/3 and b equals 2/3. Okay, I got to zoom out, get all the way up to here. You remember that we took this little fraction right here and ripped it apart into these two pieces. It was a over x minus 5. So this, because we got 1/3, it's going to be a 1/3. And b over x plus 5. And b over x minus 1. So this is going to be a 2/3. So let me zoom in so we can see this. I'm going to get rid of this, get out of the way. So this integral is equal to the integral of what I did all that work with to figure out how to separate that into two fractions. Well, it's the same as the integral of 1/3 over x plus 5 plus 2/3 over x minus 1. Notice this piece is this piece, and this piece over here is that one, the dx. And that gives me, all right, 1/3 ln absolute value x plus 5 plus 2/3 ln absolute value x minus 1 plus a c. Now, sometimes we can plug and smash these, sometimes we can't, but I know that's long. That is what this thing integrates to. You see that, like, I talk about reverse engineering something, right? It's pretty easy to go from the purple to the red here. And that, I just keep zooming out. That's a lot of work to get from here to here. In the next video, I'll show you a new way that is almost magical, that makes it so that almost all of this work can be completely skipped. I don't think this was a waste of the last 15 minutes of your life, because it's good to see where these things come from. But the next video is going to save so much time when these come up, and it's so much easier. It's quick. It saves you time. And when you take an AP test, if that's what you do, you'll appreciate it. See ya.